Sir, now we should start.
Yes, it's 40. We are starting. Very good morning to all of you, all the participants, and today's expert, Professor Rudra Ghatak. Welcome to the fourth and penultimate day of the 5-day faculty development program on sensors technology, organized by the Department of Physics, the University of Bardhaman. The program is sponsored by AICT Training and Learning Academy, ATAL, and it is also a program approved by Accelerate Weekend under DST ACRB, Government of India. So welcome. So let me have the pleasure of introducing today's presenter and expert, Professor Rudra Ghatak. Professor Rudra Ghatak is from Department of Electronics and Communication Engineering, National Institute of Technology, Durgapur, West Bengal. Dr. Ghatak, Professor Ghatak is our alumnus, another alumnus from our university. He has done his MSc, and after that his MTech, and after that his PhD from Jadavpur University, MSc and MTech from the University of Bardhaman. Then after that PhD from Jadavpur University. Then he joined NIST Berhampur. And after that, we were colleagues. He joined the University of Bardhaman for the MTech program in microwaves, what we run here. And after that, he has joined NIT Durgapur. And now he is working as a full professor in NIT Durgapur. We are very happy to have Rudra back amongst us. And always we are in touch for all sorts of academic activities, for examinations, etc. And for different type of activities, always we get help from him. And he's a very, very good researcher. And we feel proud as an ex-colleague and also being an alumnus of our university. And I hope all of you will enjoy his lecture. And his lecture will speak for himself. Once again, thank you very much, Rudra, for taking our invitation, accepting our invitation, and providing your time for us for the benefit of the participants. Welcome, and now the floor is yours. Thank you very much.
I thank you, my honorable teacher, Dr. Bose, and I welcome all the participants. Good morning to all. So I'll directly go to the presentation. And please confirm whether it is visible. I hope the screen is full. It is visible.
Yes, it's visible and full.
Okay, thank you. My discussions on the particular electromagnetic sensors would be divided into three parts. First, an introduction, which will establish the facts that why we move into the electromagnetic field domain, and particularly the RF and microwave regime. And then the certain methods of characterizing the sensors or the antennas, and what is the fine line that makes the antennas different from the sensors, particularly keeping in mind that the recent developments or the young researchers, they are working on such kind of sensors which can also transmit the data. So therefore, the sensors have a dual role of sensing as well as communicating with the reading device or the display device, or it is also broadcasted as a sensor network and a wireless sensing network. It can be wirelessly communicated to any remote display device. And the last part will be particularly some kind of applications that are into this particular paradigm. So when we call about these three parts, one has to keep in mind that what is the purpose behind a sensor. When it is a sensing technology, you can easily tell that if you all might have read some kind of elective or a core paper on radar. So it is a detection arrangement through RF radiations or microwave radiations as you look into it. So that's also kind of a sensing. So sensing has two different activities. One is into the detecting, another is measuring. So when you are specifically into the measuring part rather than detecting part, there has to be a certain more analysis and calculation that is required. So let us start with the EM spectrum that generally fundamentally gives us some idea that why we are actually into this domain. The electromagnetic spectrum, we would like to split it into two distinct categories, which is non-ionizing radiations and ionizing radiations. In the non-ionizing radiations, for extremely low frequencies, you might have seen that whenever you enter into some restricted areas, there is some metal detectors. So they are extremely in the low frequency region. They are generally used. If you see the terahertz, near to the terahertz, some high millimeter wave frequencies, about 100 gigahertz, they are being used for now. That is the concealed weapon detection radar systems. So that's also one of the systems where non-ionizing radiations have been used. Now, this is the regime where concealed weapon detection was particularly thought of, that why we cannot use X-rays, but it is generally ionizing radiations and we cannot use them because it is prohibited. We cannot use ionizing radiations on human bodies. Prolonged exposure is not there. And obviously you need to see the visible region where a simple camera, an optical camera, will be sufficient for you to monitor and sense it. And similarly, in the ionizing sections, there are some restrictions. But when you go for the baggage check counters, they are X-ray based. So if you see the entire electromagnetic spectrum, there are a lot of applications from low RF frequencies to that beyond the UV. The RF and the higher microwave region part is lucrative from the viewpoint that it is non-ionizing radiations, but there is a disclaimer here that too much exposure also you must be following the specific absorption rates to, if it's human body is concerned. If you want to probe, make a sensor for probing the human body, then also you must be following the SAR limit. So there are restrictions, but it is not that harmful so far as the ionizing radiations are concerned. I hope it convinces you the reason behind using the RF and microwave domain. Now, when you see the sensing application, one important, very old that you read in the nowadays in the class 12 textbooks are there in 11 and 12, the Hall effect. It showed that the force of the magnetic field on a current carrier, when exerted, the carriers are deflected. This deflection leads to some differences in potential differences, and that will be causing some voltage, which is very small in case of metals because of the high speed of the carriers. But it is significant so far as semiconductors are concerned. Therefore, if you take a small slab of semiconductor, it acts as a very nice measuring sensing tool for the magnetic fields. So we can have Hall effect flux meters and also the electromagnetic compass, which we also call the electronic compass. This is quite primitive, but this particular gives us the flavor that how a potential difference is directly can be calibrated to how much was the magnetic field incident upon. Therefore, when you use a sensor for finding out magnetic fields, when you want to quantize the magnetic fields, then you must also calibrate the values that for how much voltage, how much will be the magnetic field. Otherwise, it will be difficult for you to have a final readout. So the calibration is an important step when you exactly go for measuring certain quantities, either electric fields or magnetic fields, whatever you want to measure. The calibration becomes an important stage in such kind of techniques. Obviously, this kind of sensors, which senses magnetic fields, can be taken up either in the near field zone or in the little bit away from the slab also. But it has to be oriented with the magnetic field. The magnetic field should orient with that. Now, when the magnetic field orients with the semiconductor slab, when you want to sense how much is the magnetic field, it doesn't cause any harm to the material. So whenever you are testing, whenever you are doing something, we are using RF radiation for either measuring something or detecting something, it is non-destructive testing. You are not disturbing the material properties. You are not damaging the material. So therefore, this refers to some non-invasive techniques to monitor the characteristics of material, component, and structure, to measure and to detect. Now, electromagnetic sensors is a modern coinage of that particular term, though you see that one of such applications, we have never seen it as an electromagnetic sensor, but a Hall effect flux meter is a typical example where we use this semiconductor slab for measuring how much was the magnetic field incident upon. So this term, which has cropped up over the years, electromagnetic sensors, it can pick up electromagnetic waves that is impinged upon, or it can transmit certain cases in when detection stages, just like in radar, it will transmit it. There will be a reader which will send some signal towards the sensors. Together, it will take back the signals, read it, how much was it. So it's kind of a either monostatic or a bistatic radar applications can be viewed so far as its applicability. Now, when the electromagnetic sensors can be used in a purpose that you can also re-radiate the information which is there. So this is coming from the principle of reciprocity, that if it can receive properly, it can also transmit effectively. Some further insights you can get into this very old paper of transactions in MTT in 1991, where you can get some flavor of what was the reasons exactly that microwave based in EM sensing could be applied with fruitful results. The physical contact between the equipment and material under space is not required. It does not alter and contaminate, just like it is non-destructive testing. Microwave radiation propagates through opaque metal and non-metallic media. So the volume moisture content, as in aquametric, we can measure it like measuring the amount of moisture in the soil. That was one of the earliest applications where microwave radiation was used. Then again, for detection, that how much is the moisture content present in tobacco, in the tobacco industry, there also microwave radiation was used. And similarly, this regime of frequencies got accepted for different applications, either in detection stages or in measuring applications. Both we can consider it as sensing applications. One important property that it has penetration property, the microwaves have penetration properties. You might be interested that why not the higher microwave frequencies? Obviously, the optical frequencies have a good property that it has a, we can find out the material properties because of the spectroscopic properties of optical frequencies. If we move to the very high frequencies, though it is not within the paradigm of this particular lecture, because the terahertz sensing applications, which extrapolates beyond the millimeter wave frequencies, in that domain, it has the good penetration power, the penetration power of RF and microwave, and also the spectroscopic properties of optical. These two benefits are added together if you move to the high frequencies. One application for this is for detection of different material-based components in concealed weapon sections. So the spectroscopic properties and the penetration properties both can be useful when we go to the higher microwave region. This has to be kept in mind. For the lower microwave frequencies, the spectroscopic properties are not suitable. Obviously, it is relatively insensitive to environment conditions when certain frequencies are concerned, but we have to avoid the frequencies which are oxygen absorption and hydroxyl ion absorption bands. You know about that from the radio wave propagation fundamentals. So we have to take those frequencies which are not absorbed when it is getting propagated. So typical sensing applications will be something a wireless reader, a sensor. It will upload some information, try to get the information back. If you get some information back, what is the kind of information they're getting? Based on that, the decisions will be made. There are a lot of applications in certain designs. One such application which you see always when you enter nowadays in a supermarket is the RFID tags. It has a RFID reader. The transmitters, they will transmit a signal. Whether the tag is intact or not, it will send back the signal. The reader will read it that okay, everything, this information is okay, and they will give a sense that the such and such product is, it will have a particular signal identity, and it will identify that okay, this is present. So therefore, when you purchase an equipment, generally the person will tear off that tag which is attached to that particular material item that you are purchasing, and then you will be handed over that. Because if it is intact, then the probe element, or when you just pass out, the probing antennas will transmit the signal, it will get back the information. It's when you tear it off, there is no information which is got back, which indicates that the item has been sold. And if it is not sold, the tag is intact, and then it will be the reader, when it will read it, it will send a alarm beep, which indicates that some item is coming out without being sold. So this is one of the very fundamental applications of RF regime being used for such sensing applications and monitoring. Now the term sensor has been so much hyped that a simple antenna system with a receiver, because I felt that there will be the audience will have many people who will be interested in navigational systems. So the global positioning system sensors. Now instead of mentioning it as an antenna or a receiver, it is actually a receiver with antennas. It is mentioning it as, marketing it as global positioning system sensors. So these terminologies are very, very important when you understand the physical design. You take a more, you will see in the, as we proceed by the slides, if you have a small short monopole that can pick up electric fields. If you take it as, tell it a monopole antenna, you will not able to use it for EMI EMC purpose, because the engineers will tell you okay, this is a monopole antenna. This is not going to be used for these applications. But if you call it the same monopole antenna as a E-field sensor, then immediately, oh, it's an E-field probe. Then obviously the persons working in EMI/EMC will take it as granted that this is what is the equipment which is necessary for us to measure the electric field. Now, there's certain small differences in that. Their differences has to be highlighted and clarified. Therefore, I thought that if I name this as revisiting antenna characteristics, it will not be suitable. Rather, I make it revisiting EM sensor characteristics. Now, for that reason, the preliminary discussions is quite important. A sensor is a device that it can be used to detect and measure a physical quantity. They have been traditionally used in various industries. We are not interested with the efficiency because, after all, it can only detect and measure. A transducer's efficiency is important, but a sensor efficiency, 5% or 0.1%, it is immaterial, provided we know that how much is its efficiency. And in EM sensors characteristics, we'll see that if it's a good antenna, it's not a good sensor. The linearity of response, defined by plotting the output against the input, is also very important for a sensor, whether it is able to track. And therefore, when we tell electromagnetic wave sensing or speak about this, then it has to be clarified whether the sensor is an antenna. In certain cases, the sensor has to also transmit back the information. So therefore, it has to be a good antenna. If it is used for sensing of fields, then obviously we have to use a separate device. There should be two microwave devices or RF devices. One is typically working as an antenna, another is for sensing of electric fields and magnetic fields. If you are using it for detection, not for measuring the fields, if you are using it for detection, in that case, it can be a single RF device which can be used to transmit the signal, get reflected from the object, and it will pick it up. It is a wide range of frequencies. If you can do it, you can pick up a lot of information. And these kind of imaging systems have been used for tumor detections. And in fact, you will see in the certain application domain that different kind of antenna systems, how it can be used for different radar applications, for sensing applications, for detecting applications. And if it is for particularly measuring what is the quantifying the electric field and magnetic fields, then we have to answer it in a different way. We cannot tell that the EM sensor is exactly an antenna. The reason is outlined here. A device used for transmitting, receiving signal or power, it is designed to maximize its coupling to EM field. An antenna is always designed, antenna designer tries to maximize the coupling to the EM field, and is meant to intercept as much the field as possible. So therefore, it disturbs the EM field. And if it disturbs the EM field, we cannot measure the exact quantity. A field sensor, in the other hand, is an electrically small device. It can be passive without any electronics for measuring electric field or magnetic field with a minimum perturbation to the field being measured. So when you are maximizing the coupling with the EM field, in case of an antenna, you are perturbing the EM field. You are disturbing the field pattern in the vicinity because you want to communicate it. You want to radiate it. For detecting applications in the sensing paradigm, it's fine because you want to send a signal, get it reflected back for certain kind of, it can be a radar applications. But If we want to precisely, this is the fine line which is very important for us to understand. If we want to measure the electric field and magnetic fields, then a field sensor. Now, this electrically small device can be a monopole, it can be a dipole, but if you want to make it quite small, you have to think of strategies how to make it small. There are a lot of techniques which have come up by which we can make a small monopole, a short dipole, electrically small structures. But for that, the efficiency of that electrically small structure is important. Perhaps that is again, which is one of the characteristics that we are complacent about when we generally go through the antenna characteristics. So this is what one should remember, that an antenna has a good coupling, so therefore it perturbs the field around. And if you perturb it, you cannot measure how much was the electric field strength and the magnetic field strength. So if it is if it's a small loop, then it can sense magnetic fields. If it is a electric field sensor, it's a short protruding conductor, which is a short monopole. Now, obviously, the field sensor transfer functions can be theoretically determined from the measured physical properties as well as the electrical characteristics of the construction material. Therefore, our answer to this is depending on whether we are making that sensor for detecting electric field and magnetic field, then obviously it is strict no. But if you are using it for sensing for that purpose where we want to communicate a signal, and we can again get back the information of how much was what was the reflected back information and process that, then obviously we have to use an antenna for that. However, there are certain characteristics which are common when we characterize the sensors, the EM sensors. There are certain things which are common to both for antenna, and there are certain things which are particularly important for those sensors which are used for measuring the fields. So when we start with this fundamental, obviously you almost be knowing it's when it's for classroom education is fine, that obviously the interaction of the sensor with the EM field, it can measure it or it can radiate whenever there is acceleration and deceleration of charges. But it is not only the acceleration and deceleration of charges that go for the fundamental radiation equation, though it is based on the acceleration and deceleration of charges. Whenever it will be accelerated, it will take energy from the surrounding. Whenever it will be decelerating, it will give the energy to the surrounding. What is that surrounding? Though the fundamental radiation equation tells us about this acceleration and deceleration of charges, that is change in current with respect to time, we must also keep in mind the science paper which is published in the IEEE magazine in 2001. We should revisit this. If you have, you can note, and you can also revisit this paper in detail. Electromagnetic energy around Hertzian dipoles. I hope this particular information, if I try to highlight here, that the principal conclusion is that although accelerating charges may be thought of as the source of radiated fields, energy lies in the static and or the reactive field energy near an antenna and not in or on an antenna itself. No doubt, acceleration and deceleration of charges, they assist in radiation. But the vicinity is also very important. The region just near to the radiating system. Is it favorable? Is it allowing the energy to be propagated? It is allowing the energy to be stored there? That's very important. So the reactive energy near that, how it develops, how it grows, is very important for the system to behave as an antenna or an EM sensor. So if it is the reactive energy which is going there, it is able to, it is not disturbing these reactive fields. Just in the vicinity, there are some fields, electric field or magnetic field, depending on what kind of metallic radiators or receivers. It can be a probe, it can be a loop, but it can sense the fields. That sensing of the fields, if it is not disturbing the region, then it can measure, we can measure the fields. But if I want to communicate the fields to a, then this has to be perfectly favorable such that it can propagate by coupling the regions. The fields will be well coupled, and obviously we can have a chain. If you look back to a simple dipole, the fields around the current obviously will create some fields which is in the vicinity. Obviously in the free space, this fields tends to be closed curves, because in the free space there is no charges. So obviously electric lines of forces will be closed lines. Now this will produce this changing, this is a time harmonic field. So this changing electric field will produce a magnetic field. The green one is the magnetic field. And again, the changing electric field will produce a magnetic field. So it's a chain. A changing electric field producing a magnetic field, a changing magnetic field producing an electric field, again a changing electric field producing magnetic. So it's a chain. So we are able to, so this region around this particular system, this region is quite important so far as whether it will be well coupled to the fields which are getting detached from the metallic device, or the metallic device is suitable such that it can orient itself just to the nearest of this region, and then it can sense the fields, measure the fields, but far away, a little bit away. Now, how much away? That also will be clear from the regions around an antenna, though you have many of you maybe have gone through an antenna course. So there you must have seen the different regions around an antenna. There's the reactive near field, radiated near field, and the far field. So the far field distance of 2d square per lambda, where d is the maximum dimension of this radiator, that is very important here. So when you use it for detection, it is somewhere in the far field you want to create it, get the information back. But if you want to measure it, you have to be in the very near in the vicinity of the object. So it's typicality that how the fields around the electric fields are getting detached in the free space. Obviously, there is no free charges, so obviously it will be closed lines of forces. Divergence D is not rho v, but divergence D is 0, so D will be closed lines of forces. Now we can the radiation equations, the del square E, we can easily obtain from the Maxwell's curl equations and make an assumption and solve this for an electric field, and we can put the variations and invoke the Green's function e to the power minus j kr by r. This, I don't want to trouble you with a lot of mathematics, because once you understand Then when you characterize it and analyze it, then obviously you can go into the mathematics. It's just only defining, because when you define and solve for these equations, then we have to make some assumptions that how the field variations will be there. That's what is only hidden here. And obviously, we can determine how much is the field in the vicinity. Now, when it starts speaking about in the Hertzian dipole, the fundamental analysis of an antenna generally starts with the Hertzian dipole. All of us may have gone through a course of antenna engineering where we have considered the nature of the current which is flowing through this Hertzian dipole. Let us take it as I0 cos omega t, and we can get the retarded vector potential, because whenever there is a current, so there is some finite time the information will propagate, and not at a certain distance r from the source of disturbance, then we can measure almost the field. So to measure the field, this vector magnetic potential is quite important, because from there we can determine what was the magnetic field. V is equal to curl of A. So we can find what is A. We have known how much is the current, so we can easily find an expression for H. Don't worry about these equations here. Just try to understand. You will get the flavor whenever you yourself start analyzing it or work in EMI, EMC sections. Because they are the fundamental equations which you generally go through any antenna textbooks. Now that field, when it is in the far field, or we see the current distribution and we try to find out the magnetic field expression, we can see that there are a lot of terms. You can see here that is 1 by r variation, 1 by r square variation. Those all terms are present here. Similarly, once you know the magnetic field, we can find the electric field. And in the electric field, you can see that is 1 by r variation, 1 by r square variation, 1 by r cube variation. So there are certain field configurations which you know it from the static charges. That is a dipole, electric dipole, plus q minus q charge. What is the field around? What is the variation of the field at a particular distance r from this dipole? You have determined it, you have taught it in the classes. So that's the static fields. So when you determine the electric field and magnetic fields in the vicinity of the current carrying conductor, the vicinity means just near to that, what's the variation? A little bit away, what's the variation? And a little bit far away, what's the variation? That's the importance. 1 by r cube variation was there, it's an electrostatic field. 1 by r square, that term is inductive field. The magnetic fields where the 1 by r square terms are there, that is the induced magnetic field. You can get it from Bayes-Savart law. First one, you can get it through Coulomb's law. And 1 by r term, which is present here, is a far field. Now, if you tell that if r is too large, then 1 by r cube will be a very small quantity that we can neglect. 1 by r square also very large if r is very large. So therefore, we end up that in a very far distance, now how much far? That is 2d square by lambda. D is the maximum dimension of the antenna. So 2d square by lambda, you find out. Beyond that, the 1 by r variation is only predominant. Near to that, the magnetic field variation 1 by r square is the induced field. So in the vicinity of the current carrying system or the EM sensor, you can have electrostatic fields, you can have induced fields. You have to pick up that field. For measuring that, you cannot disturb these fields. So you cannot couple it largely. So therefore, you have to measure, when you're measuring the electrostatic fields or the induced fields, you can either use a probe or a loop. And if you want to sense something or detect something at a distance of 2 meters from the radiating system, a human body is there, and you send some signal and see whether there is a tumor or not, then obviously that is, you have to keep that test object in the far field. Obviously, you can solve such problems, though in the classroom educations we put up this equation. It is quite easy if you take those equations. The question queries in this way. It helps us to measure the flavor of how to measure. An Argand dipole, it's a short current carrying conductor, length of 1 centimeter, and carries a 1 ampere of current, 100 megahertz current. Determine the magnitude and phase of the electric and magnetic fields at a distance of 1000 meter away and broadside to the particular this antenna system. So you can find out that how much is the dipole length at a wavelength of 3 meter, which is corresponding to 100 megahertz, and you can find what is E theta and H phi, because 1000 meters is in the far field. So you can measure how much is the electric field, how much is the magnetic field. That's the measuring concerns. Similarly, for a loop, we can assume a small current, which is small element where a current I. We can take same I is equal to I0 cos omega t, and we can determine what is the electric fields and the corresponding magnetic fields. So here also, we can determine what is the fields at various distances in the far field and also in the near field, what will be the values. You can see the variations here. H theta 1 by r, 1 by r squared, 1 by r cubed. So you can know from if it is close, then obviously at a very small distance, which terms will be present. And if you have a very far distance, then obviously you have to neglect the r squared and 1 by r squared and 1 by r cubed terms, and we can get into the far-field expressions. And once you do that, you can find the radiation resistances of either a dipole, a loop, everywhere you can find out. You know what is the fields, you can know what is the average power from the Poynting theorem, and then you can easily determine how much is the radiation resistance by P average by RMS current squared. One thing you should note here, that if the loop is electrically small, its shape is not important with respect to the far field that it generates, whether it's a square or a circle. So therefore, in electrically small structures, there are a lot of modifications which have been possible, particularly with the use of material fundamental resonators. Because after all, loop, it's also a resonator circuit. That resonant frequency is quite determined. How much is the Q? That will also determine that how small we can make. That's also one of the characteristics we'll discuss about that. Similarly, here also for the magnitude of electric field required such that now the query is how much will be the, we are knowing how much current is flowing in the loop. You must tell us that how much is the magnetic field. So these kind of examples will help us to assimilate the fact that what is the field it can sense, and if it can sense this particular field, then how much that current will be flowing, and you can measure that current. So you can have a relationship that, okay, this is the current which is flowing in this particular loop, so this must be the field which is. So these relations, which is fundamental to the, we have already studied in the fundamental first few lectures of antenna classes, are very, very important when you generally use it in designing near field, this electric and magnetic probes. We have to revisit them. Therefore, I put these questions here. The magnitude of electric field required such that the loop carries a 100 milliampere current at a frequency of 50 megahertz The loop is a circular one with loop radius of 5.6 mm, corresponding to a square current loop of 1 × 1 centimeter. You can try it out, see whether it is 109.6 microvolt per meter of electric field you are getting or not. The relations are quite obviously, you can use this to determine it. Now, when you use the information, you pick up the information, how much is the electric field, you can pick up that particular information has to be transmitted to the device which can send it to a receiver which can process it to make it a presentable display. Easy to said and done, because when you communicate this particular information which is picked up by this sensor, by these short electrically small radiators, electrically small probes, then you have to ensure that with these small electric structures, electrically small structures, there should be, when you communicate it, it is connected to another transmission line. Universally, that is 50 ohm transmission line, because all standard category impedances are around 50 ohm. So therefore, whether the impedance is perfectly matched. To do that, you want to know about the radiation resistance, which is the real part of the input impedance. And the real part of the input impedance only remains at the resonant frequency. Slight detuned, but in a range of frequencies. If you detune it for a dipole also, you will have the input impedance of the dipole being 73 plus J42.5. This J42.5, the inductive part, generally comes because it is because of this length. If you take exactly 0.5, this length of the wire, the extended length, the fringing regions, they cause this inductive. So to balance this inductance, we generally cut it and across, make the length shorter. So exact dipoles which are used for purpose are 0.48 lambda. So we'll make it a little bit shorter, so you can nullify this inductance, which is created by this length of 0.5. So instead of taking 0.5, you take 0.48 or 0.47, 0.46, whichever is you find it suitable, such that you can omit the reactive part and keep only the real part. And you can see what is the real part. To determine that, you have to know what is the input impedance. And you know from transmission line theory how to determine the input impedance, the Zin. So you can just see that whenever you make a circuit or a component precisely with total understanding, all the fundamental informations which we have studied long ago, they're all very, very important, pertinent in design. Without these fundamentals, I think that we cannot proceed with understanding the larger picture, which is generally presented in the form of, as which we call it as, it's a very nice research topic nowadays. So this comes later, but the fundamental understanding is very important. The second part is, from the input impedance, obviously input admittance also you can get. You know from the analysis that if you know about the input impedance, you can plot it, equate it to 0. You can get the information on the transmission 0. If you have the input admittance, just flip the input impedance, get the expression of input admittance, equate it to 0. You can know what is the resonance frequency, that is the transmission poles. So we can determine the resonance characteristics of the sensing systems or the detecting systems. And finally, when it is electrically small, if you want to make it small, then there is some information on quality factor, that how small it can be achieved. There is a limit to that. We cannot make it electrically small. How much small? There is a limit to that. It's a bottom line beyond which we cannot make it small, such that it will act. We cannot use it for any good purpose. So when we proceed with this tutorial, we'll consider the network to be lossless, and EM sensor is one such circuit, where we first look into this information on the impedance characteristics, the resonance characteristics, whether it is suitable for that particular frequency or not, and then how much small we can make. This analysis can be done using the quality factor. After that, we go for the pattern characteristics, that is how the field distribution is there. These pattern characteristics include certain more information when we generally go for sensing fields in and around for EMI and electromagnetic susceptibility checking. And for certain applications where it is detecting, there obviously the radiation far field, the gain, and all these parameters, they crops up. So the input impedance, quality factor, then the information on the resonance characteristics. This all started with the transmission line theory, distributed circuit theory put forward by Sir William Thomson, which was known as Lord Kelvin. And he had another person who helped him out of to completely formulate the transmission line theory, which is the distributed circuit theory, was Oliver Heaviside, who introduced the concept of impedance. In AC circuit theory, you might have studied about impedance, V by I, but impedance is R plus Jx. It's not that only we are having resistances, impedance, and that impedance is varying with frequency. This dependence of impedance on frequency was studied and completely put forward by Shelkunov, and is known in the antenna domain. So these persons shaped the theoretical foundations on which we generally stand upon and try to improve upon our designs, but the underlying theories, they remain same. And coupled with that, when you start analyzing them for lossless passive networks, we generally invoke the Foster's reactance theorem, which tells us that the reactance slope and the suscetance slope is always positive. And this is a very important insight, because that paves the way that when we plot the input impedance versus frequency, it passes through poles and zeros. And that helps us. And this, because it alternately passes through poles and zeros, it is only because it follows the Foster's reactance theorem. And the extrapolation of the Foster's reactance theorem to the resonator concept was brought forward by McLean in 1945. So all this information is quite important to understand the fundamental concepts which are important for designing these systems. There are certain change in the terms and terminologies which we use. Now, the input impedance term, which we generally prefer to use, and all of us are conversant with, it was known as driving point impedance. It is underlined as a red line. You find that previously it was called driving point impedance. That same has been renamed. It is rewritten as input impedance. There are certain changes in this terminology. Otherwise, it's all the same. Like instead of terminal plane, we call it as ports now. So for sensing application, how much is the current which is getting flowing? How much is the potential difference when a field is incident on, when it is picking up the electric field? So this relationship between fields and voltages, relation between magnetic fields and the current, this is already existing in this beautiful relation which you see on the screen. So in the right hand side, we have the field parameters, the left hand side the circuit parameters. So these beautiful relations, they tend to relate, and this makes the sensing easy. This makes the measurement and what is to be measured, this measurement and the connectivity with the displayed results are quite easy. So we can say that this is the potential difference, so this must be the field, or this is the field introduced, so it will have this much potential difference. This much is the magnetic field, this should be the current. And obviously, this is a time harmonic in nature. So time varying electric field will produce a magnetic field. Time varying magnetic field will produce electric field. So obviously, you can relate the voltages and currents with the electric fields. Now this I want to move it forward because I think I will be surpassing the time. Let me be fast in this. I assume that you all understand about the input impedance concept. So it is only for the classroom lectures that we generally go for. Suppose it is a lossless line, we can determine the input impedance. You recollect about the formulations. Let us use it here, where the antenna system is connected to a feed line and is connected to a source. So we can find the input impedance. So the antenna is acting as a load to this. So we can determine the input impedance. The equivalent circuit finally can be obtained once you know the input impedance. We can split it up in this. For the transmitting antenna, this was the RL plus, this is the RR, which is the radiation resistance and the loss resistance. So when you know them, the total antenna resistance, and we can find what is the equivalent circuit for that. Similarly, for the receiving antenna system, we can find what is Zin, is Rin plus Jxin, which that Zin will also, this Rin will be split up into the loss resistance and the radiation resistance. So we can formulate the input impedance and for both the transmitting and receiving systems. And this helps us. For this example, we can see that a 1 meter dipole is connected to a 150 megahertz supply source, which is 100 volts and phase is 0 degree. The source resistance is 50 ohm. So the loss resistance for such dipole is 0.63 ohms. Radiation resistance, I just told you that it's R plus Jx. There is 73 plus J 42.5. So once you want to find what is the antenna current, then obviously you must know what is the V by I. So V by Z will give you. You can find what is the wire resistance. The loss resistance can be obtained from there. So together, considering the radiation resistance and the reactive term, we can find what is the antenna, and we can finally solve for the current as you see here. Because the supply voltage, you know, so you can find what is the current which is flowing. This is a typical example where the input impedance information helps you to determine if you know how much is the supply source. Now it may be that there is some field which is creating a potential difference across the dipole and the current is flowing. You can measure the current, you can get back to that how much was the field incident. So from the circuit viewpoint also you can get back. And once you know the current, so you can know how much is the power loss and how much is the radiated power. Because the loss resistance, half I square R, if I is the antenna current, R is the loss resistance, then the power loss can be obtained. When you take the radiation resistance and find half I and square R rad, you get the power radiated. Then both the information you can get. Only thing is that with this information, you have to calibrate the data. For how much it is or how much it is. Now this is generally done by the NIST USA. There are International Electrotechnical Commission, IEC. So there are certain standard organizations who have brought data over these years. What you can do, you can take up your own design and find it out and calibrate with it and trace it with respect to their data which is available. So when you characterize these EM sensors and antennas, so first thing is that whether the circuit parameters are satisfied. What was the input impedance? radiation resistance, VSWR, return loss, reflection. They are the circuit parameters. If the information is not carried forward properly, that means there is a mismatch. So you have to match it. So VSWR is important to us. To find the VSWR, you must know the input impedance, because you will not know the load resistance, load impedance. So if you don't know the load impedance, you cannot find the how much is the VSWR. Then reflection coefficients, the return loss, how much power will be returned. Now this all information in the modern day you can easily obtain through a network analyzer. For a EM sensor or antenna, if it is single port, you can connect it to the port 1 of the network analyzer. You can directly get the information. Obviously, there are certain information on the reflection coefficients. It's all narrowband measurement, because all these sensors or the antenna elements which we are talking about, these are very narrow band frequency over which it is matched. So you can find what is the impedance bandwidth over which it is matched properly. So this impedance bandwidth information is also important. Once you see that these are perfect, these are suitable as per your requirement, as per the spec, then you can move on to the field parameters and then get into the whether, okay, the radiation pattern is fine or not, the directivity, gain, beam width, polarization. Now, these all informations come into the picture. The radiation of the field parameters come into the picture. There are certain additional things like ortho angle measurements for certain these sensors in the near field, which generally picks up this information. I just want to skip to, so this is just an idea about what is the impedance bandwidth. So we take the VSWR as 2 within 2 or S11 dB, which is below -10. This is the standard way of finding what are the frequency range over which is matched. It can be matched over 2 separate such bands. It can be matched over a very wide range of frequencies. So in that case, the ratio of the higher to the lower frequencies are generally used, and the fractional bandwidth is generally considered in such applications, where the sensing application or the detection application requires very wide range of frequencies like UWB radar systems. So in that cases, we need to match it over a wide range of frequencies. Now here in this case, we discussed about the 1/r variation, 1/r square variations, and 1/r cube variations. So the field which is nearest to the current carrying element and which is with this radius r1, 0.62 square root of L cube by L lambda. So there it is the reactive near field. Then the radiating near field, which is between R1 and R2, it is 2L square by lambda. L is the maximum dimension of the antenna. L or D, in many textbooks you will find D. You can also take it as L as the length of the maximum dimension of the antenna system. And beyond this R2, so we'll have the greater than 2L square by lambda. That's the far field of the Fraunhofer region. Now let us consider this. What's the meaning, purpose behind this? I was discussing about the near field, so let us take an example where that field has to be picked up. In power electronic components require reduced switching times. This increases the produced disturbances and the systems become more sensitive to electromagnetic compatibility problems. When there is a clock, when the switch is, when these frequencies are re-radiated in a very near region, it can disturb functioning of its other components within that chip or in the nearby chip. The near field sensing technique allows to mitigate the problem by precise detection of the weak electric or magnetic fields with a micrometer resolution. And this can be employed to determine the potential electromagnetic interference source locally and spectrally. What is the frequency which is interfering and what is the location of this? So this is a probe. It's a short conductor. It's a shield. So this short conductor is picking up the fields and it can move around and it can find out that what is the source of this field which is in. Now, when you are bringing the object close to the source, because of the interconnects, there has to be certain regions where the field is escaping. That escaping field, and that too maybe it is transmitting some pulse. It may be a clock. In that case, if you take the Fourier transform of a clock, it goes to very high frequencies. If you take the Fourier transform of a sine wave, it is a single frequency. But a Fourier transform of a clock, large number of frequencies, and it may move. If a clock like this, if you take the processor, you are processing whatever the processor, the clock speed is now 3 gigahertz at max. It is getting stuck up there. Whatever the processor, multi-core also it has come. So the clock is 3 gigahertz. Now, if you take a clock of 3 gigahertz and you take the Fourier transform of that, you can well go to 30, 40, 50, 60 gigahertz. You'll find the radiation in that domain. But that electromagnetic interference can cause drastic changes in the functioning of the nearby components. So we have to first identify the source, bring a shielding for that, or we have to design the components so that they are not susceptible to such kind of fields. It offers the designer the possibility to quickly identify and correct conception faults at early design stages. We can do it through EM simulations also. Besides the MI issues, high and wide band sensitivity of the developed near field sensing system allows electromagnetic analysis, which you can take up through any EM simulation tools. A large number of simulation tools are now providing these facilities of finding the having a probe. You will find these softwares having choose a E field probe or an H field probe. Now, H field probe is a loop. Assume that it's a loop. It's actually a mathematical foundation which is inside the software which is running. So physically, you are having this kind of probe. If you are fabricating it and then using this in electric sensing probe, if you make it a loop, it will sense the magnetic fields in the vicinity. Obviously, for the far field, no need to say. It's again a bookish representation where it explains the three-dimensional coordinate geometry in the XYZ coordinate system and the r theta phi, where the azimuthal plane from X to Y, the angle phi increases again from starting from Z. If you take the point, you can measure how much is the co-latitude. So we can determine what is the three-dimensional pattern, and you can see how the field variations in the vicinity of the current carrying system is generally picturized. So there is a main lobe, there are some side lobes, there is a half power beamwidth can be obtained, fast null beamwidth. So this completely specifies that along which direction the radiation will be useful and where the radiation will not be useful if you are actually designing an antenna system. For sensors, there is some additional things which is required. This is for the detection systems where the radiated fields and in the far field radiation pattern. Now, if you want to sense a particular tumor, you cannot have a very wide beamwidth. You have to design very broadband antenna systems whose beamwidth is quite narrow. There are certain solutions of that. I will show you one example also in that domain. But if you want to sense the electric fields in the vicinity, that probe, no doubt it has to be very wide band to sense it for a very wide range of frequencies. But also, it has to measure the field components identically in a similar way along both X, Y, Z axis. To do that, the virtual handle, which is the line crossing across the diagonal of this cube, it makes an angle theta, which is 54.7 degree. If you solve it, you will get 54.7 degree. And this is the probe which you see. This is with a shield. This electric field probe or a magnetic field probe. For an electric field probe, if it can sense from very low frequency, suppose 9 kilohertz to 40 gigahertz, then obviously this particular e-field probe has to be designed in such a way that it is very, very wide band. 9 kilohertz, this is spec because it's the IEEE 1309 standard, which gives us the complete picturization of the e-field probes from 9 kilohertz to 40 gigahertz. Now, this e-field probe, this is a trick of the antenna designer who has designed it to be very broadband, and also it can, this orthoangle testing is done such that we can calibrate the e-field probe so that it can measure same value identically across X, Y, and Z axis. So this is the additional measurement that you must perform when you are using e-field probes. Now, when you if you design it for a very narrow frequency, you can just take it a short monopole along all the axes and you can take it. But they are not exactly monopoles. They have to be itself also broadband. And if you want to make it a far field, obviously you can take an anechoic chamber, or you can make an open antenna test range measurement using a transmit, a calibrated horn, and a positioner where you can put the antenna system and use a network analyzer for full S21 measurement capabilities using RF cables. And when you do that for the far fields, so you must characterize the E field pattern and the H field pattern. Typical example, we take it in the form of a calibrated horn. So let us take a horn antenna. The plane of which contains the electric field, where the electric field lies at the E plane. The plane which contains the magnetic field, you know about the TE10 modes, how the electric fields and the magnetic fields are placed. So you can individually put the E field pattern and the H field pattern and the net radiation pattern. What additionally you must know, in certain cases you must know the power flux density. For that you have to measure the how much power is radiated in the form of Poynting vector, and you can find what is the radiation intensity. It's a typical bookish way representation. I'm not going into that detailing into this, assuming that this is you must be knowing about this. And once you know the how much is the radiation intensity, radiation density, you can use it to determine what is the directivity. Now, the expressions, though it is you are conversant with, I just focus on certain aspect of this expression. 4 pi u theta phi by p right. Okay, u theta phi, you can find the radiation intensity. You know the electric fields E theta, E phi, because the far field E theta, and from the H phi you can find the phi, and you can measure what is u theta phi, but p radiated. Just see the expression for the gain. It is 4 pi u theta phi by p in. Though we had the expression for directivity, still we are very interested with the expression for gain. The difference is, one, you must know about the radiated power. The radiated power is different at different distances. At certain distances, you will have the radiated power is different. You cannot precisely measure the radiated power, but you know how much power is fed to the sensor system or the antenna system. That is, P in is known to you. So therefore, the uncertainty in the measurement is removed when we generally take about the absolute gain. But absolute gain doesn't take into account the mismatch factor. That is, the realized gain is absolute gain into 1 minus mod of gamma square, or it can be mod of S11 mod square, because the reflection coefficient is same as S11 for a single port network. So we can find the absolute gain, multiply into 1 minus S11 mod square, and get the realized gain. That information is important to us, and from there we can generally determine the directivity. So it's So gain measurements, you can easily determine how it can be done. I think 2 antenna method you must have gone through antenna engineering labs and determine how to do. But this difference you must note that it is precisely we can measure the gain because input power is known to us. Radiated power is not fully predictable, so we cannot do that. In addition to this, I hope this particular information is quite important to us. Effective antenna length, and the another one is the antenna factor. These two are important when we make it as a sensor. The effective antenna length of a receiving antenna is defined as the ratio of the open circuit voltage to the electric field which is incident in the direction of antenna's polarization. All these measurements which are there for linearly polarized signals only. The previous one where we measured the odd triangle measurement along XY axis. So this is all linearly polarized because when you keep a monopole, we cannot tell that only one monopole can pick up signals along all directions. So one monopole and the monopole, so there is another monopole. So, but they can be inherently narrowband, so large meaning. But this effective antenna length, which is required, so we can find out the open circuit voltage once you know the effective antenna length and multiply with the electric field which is present, or we can find the electric field which is impinged upon by knowing the open circuit voltage divided by the effective antenna length. The antenna factor is the ratio of that electric field or the magnetic field strength in the direction of antenna's polarization to the received voltage. What we generally specify, if you purchase a EM sensor from the manufacturers, if we tell the electric field either a loop or a for measuring magnetic field or electric field, they will provide you the data of the antenna factor. They will provide the antenna factor along with that. So once you know the antenna factor, multiply with the received voltage, you get the electric field. You know the antenna factor for this loop, and you measure, multiply with the received voltage, you can get the magnetic field strength. You can also put it in the form of the log scale. So the antenna factor includes the balloon losses, effective length, impedance mismatches, but it does not include transmission line losses. So that has to be kept in mind. This is what is the thing what is important to us. So we must be able to measure what is the matching network provided. So completely with that, you have to use a very precise RF magnetic cable to prevent the transmission line losses to corrupt your calibration data. So when you move into the small antenna, this electrically small, one term comes is the quality factor, which is energy stored by energy lost per cycle. It is classified as unloaded Q, loaded Q, and external Q. Energy stored in the resonant circuit by power loss to the resonant circuit, standalone, the separate same antenna sensor or the EM sensor. Energy stored in the resonant circuit by power loss to the resonant circuit as the loss resistance. So you can find how much is the power loss there. Energy stored in the resonant circuit by power lost in the external circuit. How much energy is stored by the antenna system and how much is the to the external circuit which is connected to the particular antenna system. And if you consider the total power loss, obviously it is the loaded Q. They are related as 1 by QL is 1 by QE plus 1 by QU. You can easily. Measuring resonator Q or antenna Q is very important in this case. For a very narrow band design, we generally have the resonant frequency by 3 dB bandwidth, we can use it. But if you are making resonators which can sense a very wide range of frequencies, that means it has a large number of modes. It can pick up a large number of modes. These modes are not harmonic in that case. If you take that, it can sense, the sensor can sense from 1 gigahertz to 10 gigahertz. it's obviously the modes. If you take the model, do the modal analysis, find the input impedance or input admittance. If you try to find the transmission poles, what you do, you find the input impedance. You know how to find the input impedance. Make the equivalent circuit, get the input impedance. You get the input admittance, equate it to 0. You can find what are the transmission poles. They are not harmonically related, these different modes. If you make a broadband system or a very wideband system, in those cases when the frequencies are very close to each other, in that case, this particular definition of loaded Q, that is resonant frequency by 3 dB bandwidth, does not hold, because the energy is power fed to the antenna system. It's not only stored in that particular F0, but it is stored in all the other frequencies, F1, F2, F3, all the different modes, which may or may not be harmonics. That has to be kept in mind when we analyze the resonator Q. Different manifestations of the Q. If we know the amount of energy stored in the electric field and the magnetic field, we can determine that. We can also determine if we know the impedance, XA by RA, with the antenna input reactance to the antenna input resistance. To determine that, you have to make the equivalent circuit and find it. Once the Q is known, you can have a clear picture. If you know the impedance matching characteristics from the VSWR, you can know the bandwidth also. This R-swell relation is there with you. To understand and slowly move on to the electrically small regime, we have to understand the radiation sphere concept, which is a hypothetical sphere whose diameter is about 1/3 the wavelength. This radius of the, or the diameter of the radiation sphere is 1/3 the wavelength corresponding to the lowest resonant frequency of the antenna. If you know that the Q is 1 by K cube plus 1 by K, this was given by MacLean in 1996. That is the quality factor, the lower limit of Q, which can be obtained if we know what is the radius A. Now, the Q can be, the antenna size can be decreased further, depends on how well we generally fill the radiation sphere with the antenna geometry. Because Chu's concern, it did not consider the reactive energy, but when the reactive energy was concerned, the reactive energy stored inside, in that case, the relation got a little bit modified. That was Hansen and Collin's expression. You can go to the paper of Hansel and Collin, which was published in 2009, a new Chu formula. The Chu's limit is there. Chu's formula was modified. The bandwidth of the antenna can be improved if and only if the antenna effectively fills the available volume within the sphere. And that is the reason that we have so many meander line antenna systems, fractal geometries. These all have been incorporated in the antenna geometry or the sensor design. It's an electrically small. Whether you take sub-wavelength resonators, a resonator lambda by 14, lambda by 60, using meta resonator concepts, from the fact that the bandwidth of this can be improved if and only if the antenna geometry can effectively fill. You can see the brown line. If effectively it can fill this radiant sphere, then only the bandwidth of this electrically small antenna can be improved. But how much it is, that lower limit is determined by the new Chu limit, because earlier it was the Chu's limit, which was this formula. This is the formula, but now we have to use this relationship. If you plot it, then the Chu's limit was little bit further down. Now it's a little bit above. So this lower bound, the lower bound which can be achieved is little bit higher up now. It's not that exciting, which was predicted earlier, but we can make it. Now we have to find which geometries are along these lower bound regions. Those are they can be effectively used to make electrically small structures, and that too they can be good sensors also. They will be very electrically small. Once they are very electrically small, we can use it for sensing electric field or magnetic field. Another term which comes into our specification is the efficiency. If you want to make the antenna efficiency, you can determine from the previous relationships you can see from here. Transmitted by P in. Now this efficiency we can measure from P rad by P in. P in is P rad plus P loss. So both parameters in the denominator can easily obtained as a, but cannot be separated easily. The radiation losses and the antenna loss resistance. To separate out the region, to measure the loss resistance separately, we have to prevent the antenna or to restrict the antenna fields in the near field region only. To do that, we make a filler cap. We put a filler cap around this antenna system. So enclosing the antenna with a conducting sphere or cylinder of radius equal to the radian length of lambda by 2 pi, the radiation resistance will be eliminated from the input impedance without changing the loss resistance. We can eliminate the R rad part without affecting the R loss, just by putting a filler cap. It's a metallic band. You can take for standard antenna systems, if you have a monopole, you can use the baby food tins. We did the measurements with baby food tin. Nowadays there are a lot of such packaging is obtained for not many such foods. You can use such tin, just fix it, but ensure that it completely touches the ground plane and it is completely enclosing the antenna system. And then you can use a network analyzer to find the Zin. So once you know the Zin, the input impedance of the antenna in free space, and with the filler cap, then we can find, once you go for the antenna modeled as a RLC, series RLC or a parallel RLC, we can use the efficiency expressions, antenna efficiency for individual segments, and we can easily make. Keep in mind that the shape of the conducting cap is not critical. The cap has to make a good electrical contact with the ground plane. It is not necessary to have the cap perfectly centered over the antenna. It gets a little bit shifted also, but it should enclose the antenna. And it's better if you use a reverberation chamber or a anechoic chamber to do such measurements. The filler cap is limited by the size of the cap when working with the low frequency. You have seen the definition of this lambda by 2 pi, radius is lambda by 2 pi, or that's the radian length, which is actually lambda by 3. At operating frequency f0, the conductivity sigma s of the shield is high enough for the skin depth delta s to be greater than the thickness T of the shield. So I told you the baby food tin that thickness T quite satisfied this. It should be more than the skin depth. And you know how to find the skin depth. But the expressions which are available for this method, they are generally for a single frequency. Narrowband antenna systems, we can measure the antenna efficiency. But the reflection caused due to mismatch has to be taken into account for extrapolating the filler cap method to the wideband frequency regime. For wideband, we have to consider the reflection of coefficient of the antenna when it is in free space, reflection coefficient of the antenna when it is placed in the Wheeler cap. So with the cap, S11 has to be considered here, and obviously S11 square in free space, P reflected by P in, with the cap, P reflected plus P received by P in. So we can find what is the power available for transmission, P in minus P reflected, and we can easily get what is P rad is P received by P rad. It is, we can put that P rad by P in terms of the S11 with the cap and S11 in free space. So this S11 measurement, and that can be done using a network analyzer, just connect it to the network analyzers. And this particular technique is useful for very broadband sensing systems. And you can do this in a reversion chamber.
Rudra, we have got 5 minutes more.
Okay. I'm just clicking out because I'm coming to the last phase. Some examples after knowing this. So it's obviously the lunch time is coming out. It's 12:05. So let us take the microstrip patch. The resonant frequency of the microstrip patch, it's a very well-known relationship. If we consider the height of the substrate is much less than the dimension of the patch, we can neglect the effective length, that the fringing fields we can neglect, and we can come up with this expression. Then we can have a analysis on the sensitivity analysis can be done on the change in the resonant frequency because change in the permittivity, effective permittivity, and change in the resonant frequency because of the change in the length. And we come up with such theoretical foundations, which is typical important for sensors, because the change in the frequency with respect to the original frequency that can be obtained using this relations. And you can see that the one side, the first term, gives us the sensitivity of the antenna resonant frequency to the dielectric constant, which generally finds its application in detection of sensing moisture, gas, because on the dielectric surface on the antenna, you can put another dielectric layer, which can be put as a carbon nanotube CNT gas sensor. So that effective dielectric, so epsilon 2, so we can have the change in the permittivity. So what should be the resonant frequency change? We can have a calibration that this changes for this gas, this change. So a lot of experiments can be done, and then we can have a complete set of guideline can be made. And the second term, where the length sensitivity, change in the length with the resonant frequency, they can be for the strain sensors, where we can measure, we can detect cracks or health of structures by measuring the bending, elongation. This can be measured. And finally, we can also go for the temperature sensing also, where the Carver and Mink paper highlights the dependence of the effective permittivity on the temperature, that is the thermal coefficient of dielectric constant of the substrate. That's very important. Again, the coefficient of thermal expansion of the antenna sensor, where the alpha T provides that what should be the, if the change in temperature is there, what should be the change in the length. So these two also can have, we can calibrate the change in the shift in the frequency with respect to the change in temperature, and thereby which is affecting the effective permittivity. Again, change in temperature affecting the effective length, that also produces the change in frequency. So this is a typical example where we can use for strain sensing, for temperature sensing, for gas sensing, such kind of antenna systems where it can be calibrated. Again, there are sensing systems where the sensors as well as the antennas are both included. So one part is sensing, and again, after sensing, that is detecting the material permittivity, that information is again transmitted by the dipole to the receiver system. So it is transmitter plus sensing arrangement. So one strain sensor, you can see the example of meta surfaces where the small patches, sub-wavelength patches with the mushroom structures, separate slicing gaps are made along the substrates, so that when it is bent, the ground plane is fixed. Now when it is bent, so individual segments with different gaps and the different length of these vias, the via produces the inductance and this produces the capacitance. So the resonant frequency is because of the gap and this inductance. The inductance can vary with different radius of the via post. But if we can make the, we can shift the positions, that is the gap may be different. So we can have identification frequencies, identical frequencies, identification 1, 2, 3 for different regions around a structure, and we can put this particular arrangement such that whichever portion which is suffering a strain, so that particular frequency will be shifted, and we can know that how much was the change in the how much was the bending. This all can be information can be obtained, and the rest of the frequencies won't change, because the rest of the frequencies are, we get the reflected frequency signature from the RCS measurement, that particular frequencies are not shifted, but wherever this particular strain is occurring, there the frequency is shifted. So this is one such example. We came up with a very wideband antenna systems for 1 gigahertz to 40 gigahertz for such kind of measurement of the tumors. We connected it to the network analyzer for the S21 measurements. Then for through-wall imaging systems, the concept is it can a large array of such Vivaldi antenna. It's an antipodal Vivaldi antennas can be put for sensing through the wall how much, what is the location of various persons inside the walls is for. Then 94 gigahertz radar systems for concealed weapon detection. Obviously, we came up with an automobile for the intelligent transportation systems, and it was in the IEEE transactions on regular technology. We used a antenna systems for detection of the blind spots. So it is actually a sensing applications where it will sense other vehicles in the vicinity, where the rear view mirror and the driver has to just turn back the head, but without turning back, it can get an indication that where is any other vehicle is there in the vicinity of the blind spot or not. So we can sense it, and again certain wideband antenna systems for medical imaging applications were also put forward. Though the EM sensors convert the physical measurements into electrical signals, and observation typical to all sensors, we have to understand the fundamentals to exactly go for what kind of sensors and detecting systems we want to make. Then antenna sensors, they have received a lot of interest in the recent years because we can wirelessly communicate with the other networks. That is, wireless sensing networks can be built upon it. Electrically small structures can be found. It has a lot of different materials have come up, like some other than the dielectric materials. We can use certain things for directly measurement of the gases. So if you have any questions on this, you can just ask me now.
Okay, so thank you very much, Professor Rudra Ghatak, for his very interesting talk, starting from theory to applications, and with very fundamental discussions, which is needed to understand the situation. Okay, so now the floor is open for questions. There was a few questions. I will read those out for Rudra to take up and answer as much as possible. And if you have any more questions, please let us know. We will forward it to Rodro and get it back from him and circulate amongst yourself. So the first question is from Jeet Banerjee, Adams University. What is the difference between the optical windows operating at terahertz frequency as compared to terahertz communications? Does terahertz communication takes place at an even higher frequency? Okay, am I audible?
Yeah, I'm getting the question.
Okay, you're getting the question. Fine.
Yeah, I'm going to question answer. So can Jeet elaborate on what is the domain of application he wants to work for? Because in which optical terahertz frequency range, that's a wide range because it is the blurring gap between the optical frequencies and the higher millimeter wave frequencies. So it's 1 terahertz, or what are the different applications? Is Jeet present?
He's present, but what happens? I've already tried to give him privilege for talking, but still now, but he can type. Prakash, you can. Yes, now you can talk. I think you can talk.
Yeah.
Jeet Banerjee, you can talk.
Jeet, what is the application you want to go for?
Hello. Jeet, you can talk now. I have enabled you, and it is now possible. Okay, probably he's typing. His answer is terahertz imaging application for detection of COVID-19 in lungs.
Terahertz means what is the frequency? See, this is the typically, if you say that it's 630 gigahertz, it's also terahertz. So that is generally used for the debris detection in case of spacecrafts. So what is the exact frequency range? Because it depends on what is the lungs anatomy. The anatomy of the lungs will govern that what is the frequency range. And after that, you can check which are the available frequency windows which are there with you, and you can use it.
Okay. So another question is from himself only. In case we are getting a negative gain at a certain range of frequencies without notching those bands, what does it signify? Impedance mismatch or radiation patterns, back lobe is being measured instead of front lobe. Kindly suggest.
Now, measuring of radiation pattern back lobe, that you can easily understand when you are setting up the measurement facility. Then obviously you know what is the direction in which you have to measure the main beam pattern. So there, I don't think you will go for a you will go do a mistake, because then it's either the designer have not understood the antenna design, or is a layman. Because when you put a horn antenna, obviously you won't go back to the other side to measure it. So it's a very unlikely. It's a very less probability that you will measure the back lobe. The other thing which you are considering, that it can be a mismatch, that can be possible, because generally for mismatch, when the signal from the generator is not moving to the antenna, there the radiation can be very, very poor, and you can get a negative gain. Another one is that antenna systems, their gain increases with the size. So if you have a very, very small antenna, that is antenna on chip, generally for that reason the antennas on chip are generally not useful, because if you make an antenna size is a very important thing. Antenna size and gainer, if you make it very, very small, the current, as I mentioned it, that it will not able to couple with the vicinity, and obviously that's too small a size. Maybe it will pick up information, but it will not radiate. I hope this will, that part was not there in your query, but this I have added because if you make a very small antenna size, those who are targeting to make antenna on chips, that is not futile. That's, if you make it a sensor, then it's fine. But if you make it a antenna for detecting, for sending the signals or for communication, I hope that will be very short and it will not be so much feasible.
Okay, so we will take up the last question because we are running a bit late. Question from Dr. Basuda. Temperature sensitivity, sir, for convective clouds, how much threshold we should need to consider?
I am actually not into this domain, so of particularly the application domain, I'm unaware of. So I hope I cannot directly answer the query.
Okay. And next thing is, many of the participants has conveyed their thanks to you for this nice talk. And with that, we are closing this session, the first session. And if you have once again from Somanath Jalal, can this physics of electromagnetic sensor be used or being used maybe, I'm not aware of, as the microscopes like scanning tunneling microscope? We use STM to study lattice structure less than 1 nanometer resolution. It's from Mr. Somnath Jalal.
Okay. The physics of electromagnetic sensors, rather than this, let us put in the question that what is the frequency? Like if you have spectroscopic application, then you have to move on to the terahertz domain to use it. That depends on what is the particular application. For that, you can try it. It's the frequency.
Okay, thank you very much, Rudra. And we are